My name's Phil Varner. I work for a company called Astraea. We do a lot with STAC API to enable data science and using a notebook, a Jupyter Notebook style environment for interacting with geospatial raster data. And I got involved with STAC about 2 years ago when I started working on an API to allow a couple of our applications to do spatial and temporal queries over data. And we started off by writing our own API because the STAC API wasn't as mature as it is now. We wrote our own API, and then about a year ago at the STAC sprint, I had the realization that the STAC API had matured to the point that it was it had nearly all the features that we wanted for our API, and was just missing a couple of things that we needed, and in many ways was actually much better than the API that we'd come up with. And so we spent actually only a couple of weeks to convert what our API was using for endpoints and formats into being compliant with STAC API. And since then, the API has matured a lot, especially through the extensions that it has defined to be a really, really great API for querying geospatial data. So I'm going to talk a little bit about that today. Most of this is actually going to be using a REST client to interact with the API itself rather than slides. So, so I'm going to quickly get out of slide mode and into actually interacting with the API. I'd like this to be very directed by the audience. So if people have questions about specific things in the API or the endpoints or the formats, the query parameters, or any of those things, please put something in the chat or speak up, and I can sort of navigate in that direction. So in general, the STAC API tries to follow a RESTful API model. It is sort of unusual in that the main endpoint, the search endpoint, is really more of an action than it is a resource endpoint like most RESTful APIs have. And also the API itself tries to follow the HATOS principles, in which the API actually allows you to easily navigate among different resources, presents a consistent model for how to navigate to different things within that API, just tries to make it so that you don't have to have a whole lot of specific knowledge about each individual endpoint or each parameter or things like that, that you can really navigate through an API and a set of resources really easily. And another I think really key feature and really great design principle that both STAC and STAC API follow is that they try to be interoperable with other well-used standards. And so this diagram here tries to show how STAC relates to other standards like GeoJSON and OGC API features, formerly known as WFS3, that a STAC item is simply a GeoJSON feature with some extra stuff in it. And then STAC extensions extend that core feature or that core item. Likewise, a GeoJSON feature collection is extended by a STAC API item collection. And one of the great aspects of that is when you do a query against a STAC API, you get back a valid GeoJSON feature collection that you can simply save and open up in QGIS or ArcGIS if you want to just look at that. So by layering these different specifications, we get a lot of tools that just get brought in for free because we've conformed to these existing specifications. Likewise, STAC is a superset of OGC API features and extends a lot of the behaviors that has and tries to use a lot of the same names for parameters, a lot of the same conventions in that, so that everything is consistent and extensible. And then I think Chris mentioned, or Chris definitely mentioned this in his intro to this whole day of outreach, in that most of STAC is intended to be a very, very small core that can be easily implemented and used, and then extensions that allow other behaviors on top of that, depending on what the user is intending. So extensions for Earth observing data, extensions for needing transactions in an API and not just wanting to read from it, extensions for all sorts of different things that easily fit into a very small core API. So I'll show a bunch of examples of that with actually looking at an API. I'll stop here for a sec to just ask if there's any questions so far, or for anybody to express something that they're particularly interested in and want to see with this. If not, I'll continue on. Okay. So I'm going to assume that everybody can see my my REST client. I use Paw here because it's pretty nice. And I'm basically just going to walk through a STAC API. This is running against Astraea's production STAC API implementation. So if you can just call it and use it. There's no, this particular version doesn't even have any authentication on it. So you can just call it and use it. So there's a root endpoint that comes from OGC features, and for STAC, there's an extension that there are two. Sorry, let me rephrase that. To use this as part of a STAC API, you simply extend the base definition of what OGC features API includes. And probably the most important aspect of this is the links. So like any good RESTful API, we have a links object that describes what other things are available in this API. And so, for example, here we see that there's a rel called search that defines where our search endpoint is. And in this case, it's /search. That's a defined endpoint in the STAC API spec that is the location to which you can do geospatial queries against whatever the backing data store is. Likewise, there's another one called collections that then links into another OGC features endpoint called collections, where we can browse what STAC collections are available. And so that's actually the next one we're going to look at. So we see two different things in this object. We see an attribute called collections, which defines what collections are available through this API. In this case, we have, let's see, how many do we have? We have 11 collections, and these actually represent the data sets that are available in Astraea's catalog. Most of these are public open data data sets. This Landsat 8 L1TP is linking to the USGS's Landsat 8 data set. Let's see what this one is. This one is the MODIS MCD43A4 collection that we've actually been generating single band cogs for and maintain as an open data set. Let's see what else we have in here. But the great thing is that we can go to this endpoint and then find out what all is available. Oh, here's Sentinel-2, L2A. Down here we have SpaceNet 7, the SpaceNet 7 challenges data. We can just navigate through here and find out what is available. In the Astraea API, the Astraea Earth on Demand UI, we actually use this to this endpoint to generate this list right here, where the user can select what data sets they want to do queries over. And then likewise for each of these, one other thing in the collections endpoint, there is, I'm sorry, this was actually not what I wanted to show. And then to navigate, to get more information about any one of these individual collections, we can go to links and see that the links have a self-rel, and then also have that we can go to, that's an endpoint that's specific to this collection, and then also an items rel, which will allow us to actually get STAC items that are part of this catalog. So I'll go next to one of the individual collections. When we run this, we actually see exactly the same thing that we saw, the same data that we saw from the collections endpoint. It's simply that instead of getting a list of all the collections, we're narrowing down to a single collection. And then in this, we also have a nice feature in STAC API where you can get a list of all the possible assets that an item in this collection might have. For example, this asset Sentinel-2 L2A but probably has an asset called band 3 60 meter. It probably has an asset a cloud 20 meter, and we can go down this list and see all the possible assets that a Sentinel-2 L2A scene might have. Additionally, we can see what roles it may have. For example, this one has a role of data, meaning that this is actually a data asset, not simply a QA asset or a metadata asset or something like that. And then we have other things that we can use, such as the extent of the data set. For example, this is Sentinel-2 L2A, so the extent is worldwide. If this data set were for something very specific, we might have an extent that was, simply a single state or a single area or a single city or some smaller subset of that. Temporal locations, so that or temporal bounds, so that we know the data sets from and to one or another times. In this case, it's 2018 April through null, which represents through the present, meaning that it's usually being continuously updated. Okay, and then within this, we see, let me find the links again. Here they are. So if we go to this rel items, which is this, we're actually doing the query to find items that are part of this Sentinel-2 L2A collection. And this returns an item collection, which is an extension of the GeoJSON feature collection. In GeoJSON spec language, the item collection is a feature collection that contains foreign members, meaning that feature collection has an extension mechanism saying just add things that look like this, and it's a valid feature collection, but you can extend it to do other things, and that's what the STAC API does with item collection. And then within that, much like well, actually not much like, in using exactly the spec for a feature collection, there is a field called features. That's an array of features and items. An item is a GeoJSON feature. So then within that, we have other things added to it, like these assets, a stack specific thing. And we can see here's an asset. It is called BO3 60 meter. It is located at this S3 URL. Size isn't something that's part of STAC, but for our specific API, we decided we should include it. So we have a how many bytes that asset is, a title so that we can display to a user what this asset might be, and then a media type for what it is. Additionally, we have a couple of geometry related fields, the spatial fields. There's a bounding box that simply says what the lower left and upper right coordinates are for this item. Geometry, and then a geometry, which is a GeoJSON geometry describing the footprint of the data. And then relevant to the API, we have a bunch of links that go to more specific things. So we have a self link that says, here's what the URL that you're currently at is for this resource. Additionally, Astraea for our API uses have added a lot of other sub-resources for this. A resource that can actually pull the data from S3, bundle it up in a zip and send it back to the user, an endpoint to get preview images, an endpoint to get a full res composite of an asset, an endpoint to do create Slippy map layers, an endpoint to do all these other things. And this is one of the nice things about the STAC API is that these aren't defined in the STAC API. They could be defined in an extension, a public extension, but we've created these and they hang on to the existing bones of the STAC API really, really nicely because it's got these resource paths. Let's see. So a newbie STAC question here is the /items query paged. I only see 10 here, but presumably some of the collections may have thousands and millions of items. Yeah, that's a really good question. And the items endpoint isn't paged, but the search endpoint is. And so I'm gonna get to that next. And pagination is actually like a really, really important part of this. That I'm going to talk a lot more about in a minute. Okay, so now we've gone through some of those basic endpoints. The real meat of the STAC API is the search endpoint. So here are several of the parameters that are allowed on the search endpoint. So I mean, it sort of goes without saying, the search endpoint, the whole point of it is to search over geospatial data that you have in your data store. It can be as specific as to a single ID, which is equivalent to using one of these endpoints. I actually realize now that I didn't actually grab one for a single item. So let me do that right now. So we see this endpoint right here is for a single item from the catalog. And likewise, we can do that with the search endpoint. We can select a single item, ID of an item, or multiple IDs of an item. We can search only on one collection. We can only search over multiple collections. These are all comma separated lists. So if I wanted to search over Sentinel L1C also, I could run that query. A bbox parameter to only do the query over a certain spatial bounds by a bounding box. There's also a parameter to allow an arbitrary GeoJSON geometry. Usually this is a polygon, but it can really be anything. So you can say, I've got these 5 points and I want any images that intersect those points. We get the temporal aspect of STAC here, where we can specify date time. And then more fields that aren't necessarily filtering over the data, but are more controlling what the API is returning. By default, the STAC API returns a limit of 10 items, which is usually pretty low. And so the limit allows you to control how many should actually be returned. So these are actually the base base options for doing queries over the STAC API. So it's a pretty small number of things. I mean, they're pretty much related to the names of items, the collections they're in, and space and time. And then extensions provide more control over what actually gets returned and increases the query power. So there's a fields extension that, if you choose to implement it, allows you to specify exactly which fields get returned. So for example, I'm gonna do a query over here, and I'm gonna say, actually, all I'm interested in is the ID field. And the result should return a much smaller object. So here I have, what's potentially a large item, especially with something like geometry in there that could be, very, very fine grained and very, very large. But I say, actually, all I want is the ID field, and I only get that, maybe a few other things that are sort of relevant, like links. That's sort of up to the implementer as to what they actually want to return. But usually the intention is that it'll only be a small number of things. Yeah, so then the power of being able to query is pretty robust with the bounding box and the date time parameters, but there are lots of other metadata fields that we may want to query over. And so let me actually just turn those off and run the query, and then we'll look at what we got back. And so, for example, let's see, in this query, I got an item back where the cloud cover is 4.8. But that might actually be too high a cloud cover for me. So the query extension allows a user to specify arbitrary common query language. That's what CQL is here. It's kind of confusing because Cassandra query language is much more common. But this is common query language. And you can specify sort of arbitrary queries over the properties in the STAC data. So I'm gonna change this here. So it says, I only want items that where cloud cover is less than 2. And then I can do requery. Oh, I didn't actually get any there. That's interesting. So let me relax my bounds. I'm gonna maybe take the spatial bound off. Oh, sorry. I realized why I didn't get any, because I had the ID query parameter still on. So it was basically querying, is the ID this single item and does it match all these, which it didn't. All right. So now I can look down here and I see I got an item back where the cloud cover is as close to 0 as you get. And these are arbitrary things. So for example, maybe one of the other examples with where CQL comes in handy is I had a coworker who wanted to do a query that was the same month of the year, but over the last 10 years. And so with this date time query format where you're saying what the start date and the end date is, you couldn't express that because you wanted to say, oh, it's between August 1st and August 31st, 2020, and between August 1st and August 31st, 2019, and between and on and on. And that wasn't expressible using this simpler datetime format. And so CQL would allow you to write that large expression and query for that very specific, those very specific intervals of time. Additionally, there's a sort extension that provides syntax where a user can sort over arbitrary properties. The most common one of these is usually the date time or created. You can imagine wanting to either sort newest to oldest or oldest to newest, or sort by the name of the collection that it was in, so that one collection that was higher quality data would be sorted before another collection that was lower quality data, or you can think of scenarios where sort by is useful. And then relevant to pagination, that's just another link in the result set. So I'm in there we go. So it's in the links at the top level. The only link you actually get back here is a link that has rel next on it that says, given the query that you just did, in this case, a get query, the next query that you need to execute to get the same results back is this one. And so I'm gonna cut and paste this in here. And it didn't really, sort of not what I wanted it to do, because Paul automatically extracted all these, but just imagine what I cut and pasted. I'll paste it in the chat. That query was in this next link. And so somebody wanting to paginate through this URL can simply keep navigating through those next links and get page after page. And then the other part, which I'm really glad we added, is post is actually a really big use case, because using get syntax and query parameters with a GeoJSON intersects parameter. So the intersects parameter allows you to send an arbitrary GeoJSON geometry and only get results that intersect that geometry. That could be possibly huge. One of the data sets that we've used on this is the STEP database that has almost 2,000 polygons across the world on it. And that's a file that's several megs and not really a good candidate for a query parameter. But there's also the option of doing a post with a JSON body. And in that case, it's easy because the intersex parameter is simply the GeoJSON representation of that, and the post handles, it handles a very large query better than get does most of the time. Difficult there is how do you describe what the next link is with post? So with that, we have a feature that gives a valid link, but adds a couple more fields to describe how the user should navigate to that next query set. And in this case, there's a parameter called merge that says, I'm going to give you a JSON body object, but I'm not going to give you the whole thing. I'm only going to give you the parameter that is the one that needs to change from the query that you just sent me. And so in this case, merge is true, which means issue that post request just like you did, but instead of sending the same next parameter that you just did, send this one. And so I'm going to cut and paste this in here. And just need to switch back to JSON. And this gave me the let's see, why didn't I get a? I was expecting to get some features back in that. But I didn't. That's odd. Well, anyway, that should have worked. But the point being that, and I've lost my. Anyway, the point being that there's a mechanism in the pagination to handle when doing post JSON to allow you to request the right next link using post. Then additionally, I wanted to show off a couple of other data sets that we have in our collection. One of the SpaceNet 7, I forgot what the whole name of it is, the multi-temporal data, global data challenge, but showing lots of different data from different places around the Earth over timescales where there's one image per month. And it's intended to be used for machine learning. So there's another STAC extension called the label extension that hooks in really, really nicely with this. And so for the SpaceNet 7 data set, we see in properties that there are several new attributes and properties that describe the data that is available in those SpaceNet 7 scenes. We have the several label attributes that say, here's what the labels mean in this data. Here's how the labeling was done. It was done manually. It's a segmentation data set. They're both building footprints. And then let's see, assets. And then we can see the assets that are available. It's these are grouped. These are 5 assets that are all grouped into a single scene, and we see how they can be linked together. We can see what the resolution of them is. We can see what type they are. various things. And then additionally, here's another data set that we've indexed, the Maxar open data set, also referred to as the disaster data set, that shows what that provides pre and post event data sets to help with disaster response in different places. This result right here is from Cyclone Fani, and shows has an RGB asset, a 3-band geotiff that can be used and has lots of different uses. So yeah, that was sort of a whirlwind overview of the STAC API. I'd be happy to go into anything more deeply or answer any questions about it now. Okay, the question is, in post requests, how does HTTP headers managed in pagination? Yeah, so I think that question is how does the client know which HTTP headers to send in the subsequent pages? Okay. The way we sort of thought about this was that in general, when a client is paginating through the API, they're going to make a request. They're then going to reuse all that, all the query parameters and all the headers that they just sent. And the only thing they need to update is the few items in the body that the user or the sorry, let me get back to the link. The only thing they need to update are probably the few fields that the server says they need to update in the request that was already sent. And so it's assumed that the HTTP headers that are sent are going to be the same for the next request as were just sent for the current request. There are some, I think there is actually a part of the spec here that handles headers specifically in case you're doing something like the RFC that defines the links headers. I haven't used that, and it's been a few months since I actually looked at what the spec defines. But there's several places in there where it's assumed that that there are many ways that you could possibly send this, whether it's in the body, whether it's in a header, whether it's in a query parameter, and helps to account for those different ways of doing it. Okay, let's go to the next session.
Thanks for that, Phil.